So looking at these quadratic functions, we've talked about all their properties really, including max and min. But let's just revisit that because this will be an important point when we do our applications. So the previous problems that we just did, we graphed and we found all the stuff, right? All the stuff was all this. Opens up or down, axis of symmetry, vertex, intercepts, and so on. So let's just take a look at the max and min one more time. It's pretty straightforward. If I have a vertex that opens up, then that means the vertex has to be the lowest point. Right? So right here, I got a minimum. That's it. If I got a parabola that opens down based on the leading coefficient, then the vertex would have to be a maximum. And the maximum is the y value. Okay, you could tell me it's the vertex, that's fine, but really it's what's the largest value here? It's the y value we're looking at, up and down. Part C, 2C, I got a graph that opens up, which means this is a minimum. Y value there, -4. And then finally for D, same idea. We graphed that. We said, oh, this thing opens down. Got to have a maximum. The y value of my vertex is the maximum right here at y equals -3. Okay, so you can get it from the graph, or you can just combine this and know what the max or min is. All right, let's take a look at some applications. So these are very applicable. We can model some real world situations with these quadratic functions, including the example we started this lesson with, which I'm going to jump to now, was this guy. Acceleration due to gravity in a vacuum is going to fall like this. The height of the object in feet is going to depend on how long it's traveling through the air. All right, so this is my initial velocity. Call that v naught. This is my initial position. And this number right here is the constant of acceleration due to gravity on Earth. It's related to that, which is actually -32 feet per second squared. You don't have to worry too much about that. That's just a little background where this thing comes from. We just need to use this thing. All right. So you'll notice this is a quadratic function. You'll notice it's the leading coefficient's negative, so it's got to open down, which means it has a maximum. Okay. So let's look at some questions here. When does the ball reach the max height? What is the max height? So it's important. I got a little bit of work over here that I started, but it's important to know that this is the vertex question, right? The vertex is input T, output H, right? So that means the first question, when does it reach the max height, is the input of the vertex. What is the max height? That's the output. Right, so this thing's going to look something like this. So when is the input? What is it is the output. Okay, so when does the ball reach the max height? I'm using the vertex formula. Right, my function was, it's not on the screen, let me put it in real quick. -16t squared plus 80t plus 40. So it's -b over 2a. -80 over 2 times -16, 2.5 seconds. What is the max height? Well, all I got to do is run it through the function, right? Anytime you have an input and you want the output, we just have, the hard part is understanding the question here is, when t is 2.5, what's the height? What's the output? So once you recognize that, it's just some simple arithmetic. Not so simple, but you plug it into here and you should get 140 when you plug in 2.5 into my height function. And just remember, we always need units for these apply problems. 2.5 seconds, it reaches 140 feet. So that means 2.5 comma 140 is the vertex. When it reaches the max height, the max height. All right, next question. When does the ball hit the ground? That's a trickier one. So when the ball hits the ground, we have to translate. The height's 0. The height's 0 on the ground. Right? -16t squared plus 80t plus 40. And now I got to solve this equation. So in order to solve this, remember, we got to go back to the last lesson. How do I solve quadratic equations? We can factor them. We can do the completing the square. We can do the quadratic formula. Which one of those do you want to use? It's up to you. I like to factor if I can, but sometimes these are, because these numbers are a bit bigger, it's going to be harder to factor. It might not even factor at all. And that's what's good about my quadratic formula. No matter what, with the quadratic formula, I'm going to be able to solve this equation. Okay? So before we do that, we can do an algebra trick. I can make this a little bit easier on myself. I'm going to divide by 4, or actually I can divide by 8. Remember in algebra, if I divide the right side by 8, I get the same equation, as long as I divide the left side by 8. So that gives me the following. 0 equals negative 2t squared plus 10t plus 40. And also in algebra, I like, when I solve these equations, I like to have my leading term positive if I'm going to try and factor it, or just if I'm using the formula. You don't have to, but it makes it a lot better. Wait, could I have divided by 16? What did I do wrong here? There's my error. 40 divided by 8 is 5, so let's correct that real quick. 5. There we go. 5. Okay, so again, I can work with this, but I'd rather multiply both sides by -1, just because it allows the first term to be positive, which I like. I don't want to work with negative 2t squared. I want to work with 2t squared, and then it'll change the signs of the other guys. All right, so I could try and factor that, slide and divide, or the AC method. But I don't think it's going to factor. I'm not sure, but I'm not going to waste my time. I'm going to jump right into the formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I got 10 plus or minus the square root of, what does all that simplify to? That's 100 plus, since I have two negatives, 100 plus 40. All over 4. Okay, so there's two answers here, right? 10 plus square root of 140 over 4. I plugged that into my calculator. I did this ahead of time. I get 5.46 seconds. And I take the minus and I plug it in. 10 minus square root of 140 all divided by 4. And I get negative 0.46. And I don't really care about that one. I'm going to throw that out. It's a solution to this equation, but it's not valid for my model, right? Time starts at time equals 0 and moves forward, so we're not worried about that. So that's when it hits the ground. All right. So now let's look at the graph and make the connection between this application problem and the problems we did before without an application. It's going to start here, goes up, comes down, and stops here, right? The domain will be limited to just positive inputs and outputs, positive time, positive heights. Nothing else would make sense. This is the max. It happened at 2.5 seconds and 140 feet. This is my x-intercept, or my t-intercept in this case. This is 5.46 seconds. And this would be the y-intercept of, what was that, 40. Okay, and then if I ask for a domain, we could do that because I'm looking at it. 0 to 5.46, and I guess we'd include both of those. And we could even do the range. 0 to, and we know what the maximum is, right? Because we have the vertex 140. All right, I got one more application. Let's take a look at this next one. A backyard farm wants to enclose a rectangular space for a new garden with her fenced backyard. She's got 80 feet of wire fencing to enclose 3 sides, and she will use a section of her current fence. So here's her current fence. And then she's going to say, all right, I'll use that fence for one side to save me some fencing. I'm going to go 3 sides. All right, so that's the scenario. We'll call this L. Find a formula for the area enclosed by the fence if the sides of the fence perpendicular to the existing fence. So that's perpendicular. That's going to help us because we got a rectangle. I'll call the width W. Okay, so does it make sense if you got 80 feet of fencing, this plus this plus this is 80. So that's W plus W plus L equals 80. But that's not the answer to my question. I need the area. The area is length times width. So I got a problem here, right? I need a function of one variable. I got 2 variables here. I got an L and a W. But I can use this first equation with the given information about the 80 total perimeter, to solve this for L, think about this for a second. I'm going to solve for L. And if I solve for L, I'll just have a function of one variable. Let me show you what I mean. I'm going to subtract 2w, doing a little bit of algebra. So this is L, 80 minus 2w. I'm going to plug it into here. So my area function is now a function of width only. Oh, I'm going to plug it into, sorry. I'm going to plug it into here, right? Because that's L. L equals 80 minus 2w. So 80 minus 2w used to be L. Now it's 80 minus 2w times w. So my area function then, if I run this through, will look familiar to you. It's negative 2w times w, that's negative 2w squared. And then w times 80 is plus 80w. So now with a little trick of substitution, you can write using function notation. It's a function of w. And it's negative 2w squared plus 80w. That's the hard part. All right, that's the hard part. We had to use this other information in order to get a function of a single variable. And look what happens. It turns out to be a quadratic function. So you know that it's going to have a maximum area, right? Because if you think about it, like we could have w equals 5. Here's one option for the fence. And if w were to be 5, we've used 10 feet of fencing. That means this would have to be 70. But it'd be like a really skinny area. And it wouldn't have a lot of square footage, right? So you could also do, well, what if the w was 10? Right? If the width was 10, then I've considered 20, and then this would have to be 60, right? So that's a little fatter, and that'll change the area. The area would be 60 times 10, that's 600. So what w makes that a maximum? Well, we know the answer to that, or we know how to do it, because it's a vertex question. Again, it's a vertex question, maximize. All right, so the width that maximizes it would be w equals negative b over 2 negative b over 2 times a, right? I forgot my vertex formula for a second. Negative b over 2 times a. There we go. So it's going to be 80 divided by 4, which is 20 feet. So I was just kind of guessing and trying to figure it out. But I know by my math that the 20 is going to maximize my area because that's the maximum of my parabola that's modeling this situation. So if we've accounted for 20, then this has to be what? You can use your formula if you want, but we can kind of figure it out from the picture I got. I got 80 feet of fencing, 40 is accounted for, so that leaves me with 40 left, right? 40 plus 20 is the original 80. So to answer the question, the width has to be 20, and the length would have to be 40, and we need our units. And that is how we use the quadratic function to answer this maximization question.